This video will show the basic functions for layout and routing. We'll learn how to add mechanical constraints from code, how to add copper pores from code, how to fan out components for routing, and how to create and modify auto-routed traces. Let's start by setting up a few mechanical details for our board. We'll need to expand the mechanical outline, so let's change our shape to be 100 millimeters wide, and say 70 on the vertical, and change the corner radius to 3.0. And this can obviously be any shape, including imported constraints. If we save and run that, beautiful. You can also fix the location of components from code. So it's quite common to import a set of constraints from mechanical and turn those into code. Often you have outlines, mechanical features like mounting holes, and component locations. So if we select this USB and press E to bring up the name, we can see that it's core.usb-interface.usb.j. If we wanted to add this at the top level, we would say, you can make this public so you can refer to it in other modules. And here we would say place and paste that name in. And let's give it a location. Location, say 10 on the X, minus 30.5 on the Y, and is on top. And when we rerun the design, this component has now been locked in code. So it treats code as a source of truth for the design. As the next step, let's add power and ground pores. So I'll make these nets public. We'll need 3.3 and ground. And here we make a geom. So from code, you can actually make any possible copper geometry, any layer that you want to. Everything's fully scriptable. So here we're just going to use that to create some pores that are the same shape as the board. So say geom of the ground net is going to be a copper pore. And this, we say layer index 1, so that's inner copper 1. Same here. Give it a isolate of 0.125 and a rank quite low. And the shape of this is going to be the board shape. This is going to be a 4-layer design. I like having both inner layers be ground. So we'll change that to 2. And we'll also create a power pore on the bottom for the 3.3 volt net. So that's layer index 3, I guess, for the bottom. Okay, yeah, all right. We'll have to get the core.ground and core dot that one. There we go. So we're referencing the nets from the top level into the communications core. Okay. So the pores have been added to our design. They're not rendering because there's nothing connected to them, which we will change shortly. Let's move on to placement and routing. For the rest of this video, I'm going to pop out the board in schematic views. The model in JITX is to select a set of things and then do something useful. For example, let's select all the bypass capacitors for the FTDI. So I'll hold down Shift and drag a box here. Grab these two as well. Hold Shift and double click to share the selection to the schematic, to the layout. And now I can move these around. Click and drag to move. Press R to rotate. Shift R to rotate the other way. And F to flip to the back of the board. Now with copper geometry belonging to 3.3 volts, the bottom pore is rendered. There are many other selection tools available. You can see them in the question mark menu, which holds all of the commands. One helpful one is U, so you can select, for example, the EEPROM. And if you press E, you see this is the EEPROM component in the EEPROM module in the controller in the communications core. So if you press U, you select all of the components in that module. And if you press U again, you'll select all of the components available in the communications core. So a very quick way to use the hierarchy in your design to quickly select things. One notable aspect of circuit boards is that they often have more than one layer. So let's learn how to do operations on other layers and adjust layers like silkscreen. The layer stack is on the left-hand side of the screen. This highlighted layer shows us what copper layer is currently active. We can change the layer by clicking on it, and you can also move up and down the layer stack with W and S. Another layer we can work on is silkscreen. If you select the silkscreen layer, you're given a tool to help you reposition your reference labels here, which will then move with the origin of the component. Let's move on to fanout and routing. So as a user, you will choose which signals get routed on which layer and how those signals transition. So for example, let's take this ESD diode, move and rotate it down to the USB. We can select the ground pads, shift click, and press Shift V to auto add vias. With those vias on ground added, the ground pores on layers 1 and 2 are now visible. This is what we call fanning out a component. You add vias and connections and other geometry, which will then move with the component. So notice as I move this component around, the fanout moves with it. Other types of fanout geometry include differential insertion points. So if I select these pads and press Shift I, we add differential insertions where the pair goes from single-ended to double-ended. And again, those move with the component that they're created from. So that's fanout. Let's move on to routing. To route, you select a set of pads and press Q. Similarly, you can select differential insertion points and press Q, and the pair will be routed between those insertion points. Notice that everything is auto-routed here, so as you move the components around, its fanout geometry follows, and the routes will also follow and get recalculated when they need to be. You can also control the direct path of a route, so let's move our EEPROM out of the way, and we'll bring our FTDI chip down here. Again, Shift I, insertion point, select and press Q to auto route. So let's place our crystal, resonator, and its capacitors. And looking at this circuit, we also have a current limiting resistor. Okay, so here we can select these pads and press Q. We get an auto route, and let's get our resonator in place. Its load balancing caps. Select our ground pads, press Shift V to get vias, and let's select this pad and press A. So A selects all of the pads on a net. With those pads selected, you can press Q, and again, press A to select all the pads, and press Q. Now, this has created what I would like to call a terrible route. So there are several options for fixing this. You do this from manual routing mode, so which you can press this button up here, or press Shift Q as a shortcut. So first, it allows you to reroute routes that you don't like the path of. So here, we change the path of that route, and notice it'll follow topologically, right? So it's only going to avoid the obstacles in the shape that you indicate. Another option is you can create routes manually. So if you press Shift Q again, start on a pad, it will show you the destination pad, click to finish the route. And another option for manually controlling routes is to add control points. So this is a control point. So if you select that and then click on a route, it adds a point that the route must pass through. So if you, for example, wanted to control where this route exited this pad, you could use a control point to force it. And there's automation you can add on that later. Finally, you can also manually adjust routes. So let's, for example, say that we don't like the default dimensions for this oscillator trace. We will want to increase the clearance to, let's say, 0.3 millimeters. You can do that from this edit menu, where you can create the routes and then go in and edit them to create geometry that we're happy with and use up the clearance for better layout performance. Just like in the schematic, we can use commands from in layout to automate our work. So let's demonstrate on the bypass capacitors for the FTDI chip. So we move those to the bottom here. So we can gather those up. So let's start by, we'll space them out. So I move this here, select them all, align, and then distribute. We've not got all our capacitors in a row now. So if I selected all of these and pressed Shift V, it runs the auto via command, where it automatically adds vias in a direction from the pads. And in this case, this is not how I like the vias on bypass capacitors. I rather want them directly to the side of the trace, to the side of the pad. So let's delete those. And instead we'll run a command that allows us to add more control. So open the command panel with backtick. We'll say auto via, you give it an angle, here we'll say 180, and a distance, 0.1 millimeters. And now all of the vias have been added to the capacitors in the style that I prefer. So you can use commands to get in and then customize your layout and your layout experience to workloads that you find productive. Similarly, you can select all of these and change the trace width to, let's say, 0.2. And we now have some capacitors that are ready for placement. Again, we can use a short trace to guide our placement. So if I exit this, pressing A on this net, you can see that there are multiple capacitors bypassing this net, bypassing each of the pads on this 1.8 volt power net. So these turquoise lines indicate which pad these capacitors go with, because we know more than just naive information about our design. Rather, we know exactly, with the short trace annotation, which capacitor that's meant to bypass. So we can just easily move these capacitors into place by following the guidance from the short trace. And this is very helpful as you start scaling up from one set of capacitors to several tens or hundreds of capacitors. Let's switch layer to the top. Let's complete the bypass routing on this FTDI chip. So we select a ground pad and press A. We can see that we need a few more vias created. So just selecting these and pressing Shift V, because the ground pads are not always adjacent to the vias that we'd want them to be. So that looks pretty good. So now we can select these and route them. If we wanted to, let's say, force this connection out, hold Shift Q, add a control point, drag that out, Shift Q, add another control point, and force it to be in the style that you prefer. Route that, route that. Okay, looking pretty good. And as before, you could select all of these and adjust the trace width to 0.2. Let's finish this layout and learn about more about UI commands and alignment at the same time. If we take this EEPROM chip and we'll select its pull-up resistors there, Shift double click, move those over to be in the vicinity. Run the auto via command on our bypass capacitor. These aren't quite where I'd like them, so you can select and then hold Control to drag, and you get angle-based dragging. And then we'll move this capacitor to be roughly here. Route. Let's get these resistors roughly aligned. Okay. As before, you can align and distribute these to get even spacing. Select all of these, press A and Q to route them. And if you want, adjust the signals. Now, let's say we wanted to align pads of things and not just components. Let's make another command. So there's one called align first. So we say align and give it the option first. It's going to align that resistor to the first thing that I had selected, which is in this case this pad. And we can also customize the interface. So we can say bind B, align first. And then by selecting these two and then pressing B, we've now moved that command to be bound to the B hotkey. And let's use that to finish off the routing. So we'll select our power filter components here. Got this ferrite. And the capacitors. Flip those to the bottom. Go. And as before, select these, press B to align, select these, 1, 2, 3, press B to align, and you select a net, press A, press Q, and then press Q here as well to route the unfinished connections. And as before, we can select all these, make sure we have balanced copper by using a 0.2 millimeter trace width. And these we can align as well. Why not? Let's finish off the place and route of the FTDI. Can select the component, press U to select all it with its bypass capacitors and move it off a little bit because we need to make room for the resistor. Notice that, select these, press B to align, Q to route. And because everything's auto-routed, we can have some flexibility and figure out the overall flow and then detailed placement later. And feel free to apply what you've learned to tidy this layout up to your own preferences. In the next video, we'll show how to add the power supplies for this design and how to automate power routing in JITX.